Okay, suppose we have two pool balls that collide head-on, both moving along the same line, so we could have a little dotted line here that we call the x-axis. Okay? Then they collide, so before collision, they're moving like this. After the collision, well, let's say that the 3 kilogram object moves off in this direction at 4 meters per second. And the 5 kilogram object has some unknown velocity. How are we going to determine the velocity? Well, Newton's third law, the law of action-reaction, says if you and I collide, hopefully not at too great a speed given my frailty, if you and I collide, the force I exert on you is equal to the force you exert on me, but in the opposite direction. So that's true anytime two objects interact, anytime two objects exert forces on one another. The force exerted by one object is equal and opposite to the force exerted by the other. It's the law of action-reaction. Okay, well, Newton's third law applies to the net force of, let's call this mass M1. Let's call this mass M2. Let's call this velocity V1. Let's call this velocity V2. So M1 is this, M2 is this, okay? After collision, well, you still have M1 and M2. That hasn't changed. I'm going to call this velocity U1. I'm going to call this velocity U2. Well, the other thing I've got to do, since I'm calling these velocities, they have directions. So velocity has a direction, velocity is then a vector. Okay? If the x direction is here, then V1 is 4 meters per second times the I vector. And V2 is 6 meters per second times the I vector, except it's negative. Because, of course, we're moving in the opposite direction. The I vector is a unit vector in this direction. So there we have it. Okay. After collision, U2 equals 4 meters per second times the I vector. And U1 equals what? Okay. Now, by Newton's third law, F net on M1 equals negative F net on M2. So I'll just say that is F net 1 equals negative F net 2 so the impulse in M1 equals negative impulse on M2, because obviously the forces these things exert on each other last for the same time. They're equal and opposite, so the impulses have to be equal and opposite. From that, it follows, well, I really didn't want to say it this way, but I guess I still have to. No, let's say it this way. Okay, so M1 times U1I, which is the final momentum on M1. And I don't need the I right there. So let's take that away. I already made the D1 and U1 into vectors. I don't need that double vector, do I? It's the negative of M2 U2 minus M2 V2, just by the notation, okay? Which means then that U1 okay, so M1 times U1 minus M1 times V1, V1 being 4 meters per second times I, has to equal the negative of M2 U2. Of course, that's your final velocities. That's times 4 meters per second I minus M2 times negative 6 meters per second times I. So that M1 times U1 minus 4 meters per second times I equals M2 times, now this, well, this is go ahead, I times negative 4 meters per second times I plus 6 meters per second times I. Now this term is then going to be equal to, well, we have a numerical result here. Okay, this is 2 meters per second times I. Now to solve for U1, I have to divide those sides by M1. Over here we're going to get U1 minus 4 meters per second times I. So that U1, which is the velocity of the 5 kilogram object after collision, so U1 is this, okay? Now M2 over M1 is the key quantity here. I didn't put the numbers in, but I'll talk about that ratio. M2 over M1 is 3 kilograms over 5 kilograms, right? Which is just 3/5. And remember that 2 meters per second times I is the known change in the momentum of the second object. I'm not going to go too deep into interpretation here. We just want to kind of get the idea of the method and the relationships down. But we take, since this object has only 3/5 the momentum of this one, the effect of changing the momentum of this one by the amount you do is only, on the velocity of this one, is only 3/5 of that change. And we can see that this is going to be 6/5 plus 4. That's going to be, well, let's say 1.2 meters per second times I plus 4 meters per second times I. Okay. Now, the 4 meters per second times I, something's wrong here because I got a wrong sign or something. That's clearly in this collision, when this mass hits this one and reverses its direction, this mass is going to slow down. So something's wrong here, so check my numbers. This is the original velocity of this thing, and this should be its change in velocity. I think I've got all my signs right. The change in velocity should be much different than what I've got. Okay, anyhow, this is the original velocity. This should be the change in velocity, and this should end up as it ends up. We'll have to see how that works out.